Let's talk about the oxyheme dissociation curve. This graph is really a comparison between two factors that we're going to talk about and concentrate on most. It's really three factors, but we're going to concentrate on the PO2 and how the partial pressure of oxygen influences loading of oxygen onto the hemoglobin. First, you'll start out by hearing P50 mentioned several times, and we'll talk about what that is, but mainly what you want to do is you want to say, well, if the blood's environment is normal, then there's a certain relationship between PO2 and saturation. An example would be a PO2 of 60. If I went straight up to the red line and straight across, would yield a saturation of the hemoglobin of 90%. And we can pretty much bank on that being the case if the blood's environment is normal. And we'll talk more about that. So the relationship with normal pH and CO2 and that kind of thing in the bloodstream, as long as that's happening, then you're going to have this relationship of PO2 on that side to saturation on this side. So the normal PO2 of 60 will yield a saturation of 90, as I said before. Now notice that you're not assigning any kind of a symbol to the PO2. You're not saying venous or arterial, because one of the other things you want to take into account is that a PO2 of 40 is a saturation of 70. That's describing venous blood, because venous PO2 is around 35 to 45, and venous saturation is normally 65 to 75, and if you take the mean of each of those ranges, then you get a PVO2 of 40 and a SVO2 of 70. So this is maybe one of the most important parts of this whole talk, and one that's clinically useful. So pay attention to this where we go. This is going to come up over and over. All right, it says that the safety zone for PO2 is about 60 or higher. So we don't like to see the PO2, PaO2 drop below 60 in patients. That's the minimum safe amount. That's equivalent to a saturation of 90 as a minimum safe saturation. All right, hemoglobin moves through the alveolar capillary system and is oxygenated, and diffusion occurs, and you can read about that. All right, an increase in PO2 above 100 really adds very little to as far as oxygenation goes. A reduction in PO2 less than 60 causes a rapid decrease in the amount of oxygen bound to hemoglobin. So that's when you look at the oxyhemoglobin curve, then you'll see that the steep portion of the curve represents lots and lots of loading of oxygen, and then when it flattens out, the hemoglobin is basically saturated with oxygen, and that's what that's talking about. So now we'll talk about the shift of the curve, but here's P50, as we talked about before. P50 is the partial pressure of oxygen that it takes to saturate 50% of the hemoglobin. And the P50 is normally for a normal adult in a normal curve, a normal blood environment, it's going to be around 27 millimeters of mercury to get 50% of the hemoglobin saturated, and that's what these arrows are depicting. Now there are things that shift the curve to the right or to the left, and let's talk about what those factors are. Here are the factors, and what you're going to need to do is know what direction the factors move in order to shift that curve. Now the shift of the curve to the right is going to basically cause there to be a requirement of higher PO2 to saturate the same amount of hemoglobin. I'll give you an illustration. This is a rightward shift, and let's say a decrease in pH, increased CO2, that's respiratory acidosis, or any kind of acidosis would shift the curve to the right. So we'd take that same 60 PO2 we talked about earlier, we go up to here to the rightward shift, and across, and you barely have a saturation of, say, 70, almost not even 70%. Remember, before it was 90% saturation with normal blood environment, but when you didn't have acidosis or whatever, anything like that. So one of your challenges is going to be to know the factors that shift the curve to the right, and I would memorize this by saying that it's a decrease in pH or acidosis and an increase in everything else. PCO2, temperature, 2,3-DPG, etc. All right, and then with the leftward shift, it's the opposite, and you would have opposite factors doing that, and that's basically where the question is going to come from. So a story that you might want to remember is that if you were the oxygen molecule and you're trying to be pushed into acid, this acidic pH, then it's going to take more partial pressure to push you in. So loading at the lungs is going to be difficult. That's what we just said, that the partial pressure requirement is higher. Loading at the lungs is going to be difficult, but if you're the oxygen molecule and you're in acid, once you reach the tissues, you're wanting to get out. So oxygen unloading is good there, and we want, that's what happens. With a leftward shift, you think of a fluffy cloud, and with a fluffy cloud, basically, if you're the oxygen molecule, it takes very little pressure to push you into that fluffy cloud. So basically at 60, now I have a saturation of 95%, so I'm pushed into the alkalotic blood, the blood with high pH, easily, and so the partial pressure to push you in there is less because it's a fluffy cloud. And once I get to the tissues, though, I don't want to get off of the tissues because I'm in that comfortable fluffy cloud, if you would. So that's a way to remember it. I'm not sure how effective that would be, but basically for the test, if you'll know what factors shift the curve right or left and the effects that those have, that's the main point. All right, so that's an important idea, and just read about the shifts right and left, and what the oxyhemoglobin curve really is comparing is PO2 and saturation, and that's the main point. Our next topic is going to be arterial venous oxygen content difference, and we'll talk about that next time. Thanks a lot.